Good evening, everyone. Welcome to today's problem solving section, course Digital Design with Verilog. So, week 5. Today we will see the Verilog coding. So, Verilog is a hardware description language, HDL. So, its syntax is similar to C or C++, and it helps us to write, like if we have, say, just a NOT gate, we can define at the transistor level. So this is a NOT gate using the CMOS logic. So we can define it using at the transistor level. But as the design grows, we want, like, the designs contains billions of transistors. So we go for the design using Verilog, where we can write. We have three types of modeling. So first is what is the hierarchical design concept. So we first break the circuit into submodules, the design into submodules, and we can start from the top module to the top down approach or bottom up approach. So here, if we want to design a counter, ripple counter, so what is the T flip flop does is it is a toggle flip flop. That means if the input is T flip flop, if the input and the next state, if the input is 1, next state is 0, and if the input is 0, the next state is 1. This is the toggle flip flop. Now if we have initially reset all the four flip flops, then next, so this we apply a clock, and because of this toggles and other flip flops remain the same. So this is a, this means it is a edge triggered flip flop. So this every clock cycle it is toggling, and it is ripple because this output will act as a clock for the next flip flop. So next, to design a D flip flop, we can take a D flip flop, and D is the same output. Like for the D flip flop, the input, which is the D, and the output, next state, if it is 1, the output is 1, and if it is 0, the next state is 0. So to design a ripple counter, we need 4 flip-flops, 4 T flip-flop, and to design each T flip-flop, we need a D flip-flop plus 1 inverter. So if we have a 1 has the input, this will be 1, and the input to the NOT gate will be 1, so output is 0. So this is 0, so the next clock cycle output will be 0. So in this way we will toggle flip flop. So whenever reset is 0, the output is the toggle output. Now if you want to write a, like, let's start some example of a Verilog code. So let's write a Verilog code for 4 to 1 marks. So what is 4 to 1 marks? It consists of two select lines, S1, S0, which selects between I0, I1, I2, I3. So select 0, 0 should select I0, 0, 1 should select I1, I2. So now here we can observe we need some conditional statement. So let's use a switch statement, that is a case statement. So first, any module in Verilog should start with module name. So this is a user defined name and the port list. So here itself you can define the port, whether it is input port or output port, or let's just list the port names. So it can be output followed by input or input followed by output, and end with semicolon. So this consists of, okay, let's complete it. So now we have to define what are the inputs and what are the outputs in this port list. So inputs, the select lines are the input, and what is the output? Sorry, inputs again we have IN 0, and the output is to store some intermediate register, we need OP. So now we will use procedural blocks we call always. In procedural block we have always and initial and begin. Always block execute, like always block, whatever the statement inside the always blocks are executed like repeatedly. Initial and begin will be executing only once. So at the rate, this we call as the sensitivity list, or whenever any value in this list changes, then the statements will be executed. So we want whenever either or any of the input or the select line changes, we want to execute this statement. And if we have want, like in C we have this, so in Verilog we will use begin and end if we have multiple lines of code. So I have, we need a case statement, and we have to select lines, so we have to choose between with select 0 and select 1. So this is concatenation operation, select 0 and select 1. So if this means 2-bit number which is binary 0 0, then the output, and this is an assignment statement. This also we will see we have two types of assignment, blocking and non-blocking. 0 0 means in 0. 0 1 means in 1. And if not any of these cases, we have to like write a default case. And we have a begin and end, so end. And to end the module, end the module. So every module we have one end module. This is the end of the module. And this statement, this is a procedural block. This not RHS, LHS, the procedural block should be of reg type. Now we will see what is reg. And this is the module name and port list. These are the declaration. So in this sample code, you have any doubts? So now we will see structure of a module. So we have to start with the module keyword, and the module ends with the keyword end module. And the module has a user defined name, module name, and consists of port list, ends with semicolon. Then we have declaration, where we declare the input, output, input. And this also includes any intermediate outputs, registers or wires. Then we have the statements inside the procedural block, initial, always. So if we have multiple lines of code, we use end and begin. So this is the module, how we define it in the Verilog. Okay, next, ports. What is a port? If I have a Verilog module, like say we have three inputs A, B, and C, and this is some module, and we have the output X and Y. This is the output, this is the input. So the ports, now in the input ports we have to define A, B, and C, and output will be X and Y. And some ports can be bidirectional, both input and output. Such ports we will define with in-out. Now, by default, the input and output ports are of wire type. That is, like, they are continuous assignments and not any storage element. Next, model instantiation. Say we have a D flip-flop. We call this flip-flop, instantiate this flip-flop to design a T flip-flop. So that we call as the model instantiation. This is the instantiation. Okay, so now um, what does the Verilog, like once you synthesize this code, that is the tool, synthesis tool will map to the existing technology library and will convert this to the gate level, to the standard cells, like, and not like gates. So now this DFF, if we assume that we have already defined this code for this D flip-flop, this T flip-flop, and if we synthesize this, we will have an hardware for one D flip-flop. So if we instantiate it two times, call it again next time, then we will have two times the hardware of D flip-flop. So that is the instantiation. And now we have the output Q and the input is clock and reset. Clock, reset. These are the input and Q is the output. And we have an intermediate value, this D, which is wire. Okay. Now we pass output followed by input if we have Q, D, clock and reset. And this, what is D? It is actually the not of Q. So, and what is this not? Verilog, this is the primitive. Primitives can be both user defined and existing in the Verilog. This is not is already defined in the, we can use it directly for the NOT gate which has output followed by input. So now we want to instantiate this 4 times to design a 4-bit ripple counter. So let's start. So first we have to start with the module, and name of the module is ripple counter, and the input Q, sorry, port list is this Q which is 4-bit clock and reset. So this is the output, these are the inputs. And what is the output? We want to design a 4-bit, so 3 down to 0, 4 bits, Q. And input clock at reset. For single line comment, this is the symbol. and this is for multi-line. Now let's instantiate T flip-flop, T of 0, Q of 0 is the input, clock, and reset. So to access 4 bits, we can access by Q of 0, Q of 1, Q of 2, Q of 3 for the 4 bits. So the first flip-flop output is the clock to the next flip-flop. And for every instantiation, we need a name of the module. So this will create 4 T flip-flop hardware. So is this code clear? Okay, value set in Verilog. What are the values any node can take? So for example, consider a NOT gate. We have defined this as say input, and this is say wire some node Z which is not connected. So in that case, if it is at the high impedance state, we have Z in the Verilog, and similarly 0 and 1 and X. Say we have this node driving to 1 by some network here, and some other network here drives this to 0. This net value, it will be in X, or don't care, this is okay. So this X and Z are undecided values. Okay, next we will see for a single line command we have this is the operator, and for multi-line command this is the operator. So further we have unary operator like not, negation, binary operator say and or, and ternary operator. If this is true, select C, else select D, and this is sent to A. Something like this. This is equivalent to a multiplexer. If this is true, select C, else select D, and this is C. Yes. Okay. Next, any numbers we have to specify. We already seen. We start with what is the size of the number and the tick mark. What is the base number of the format? like H for hexadecimal, B for binary, O for octal, and what is the number. If we have a sign, we will represent here in decimal. Okay, so this I am removing. Let's see. So if we have 4-bit binary, value is 4 ones, 12-bit hexadecimal ABC, 16-bit decimal 255, and we specify D for decimal, H for hexadecimal, and B for binary, and small o or capital O for octal. Okay. Next, number specification. Numbers that are specified without this base of the number are decimal numbers by default. Okay, so by default they are decimal if you don't specify the base. Numbers that are written without size are by default um, specification have a default number of bits that is simulator or machine specific and like at least 32 bit. So this is doesn't have any base or the size. So this is 32 bit decimal number. Similarly, this has H hexadecimal, no size, so 32 bit hexadecimal. Again, this is octal, so 32 bit octal. So if we have a negative number, as I already said, like we can represent sign here at the beginning before the bits number of bits. So minus 3 is represented as minus 6 tick D 3, and this is not allowed. Like specifying this. Okay. Minus 4 size tick D, this is valid. Okay. So next, Verilog components, we any intermediate values if you want to store, we can use wire or registers. Wire are continuous assignments, connection between the components, and registers represent some storage element. Okay, and we also have arrays of this storage element. We call that as memories. Okay, so net. Say this is an intermediate value which we want to store so that we can apply to the next module. So this can be a wire. So net represent connection between two hardware element. They are always driven by some source. And if can you float any net, hanging net, so we have already said that here, if you float this net, it will be in the high impedance state. So if you float any net, it will be in high impedance state, or it will have a value Z as the default. So this always needs a driver. And registers are data that always retain this value until the next value is placed. So registers do not, like, it is like storage, so it need not have the driver all the time, like continuous assignment. And the keyword is reg. Here the keyword is wire, and it can hold one of the four values. By default, if you don't assign any value to a register, it will be in unknown state X. Okay. Now vector, register or net, can be declared as vector that is multiple bit. This is a bus of say 4 bit. So you can have, say this is a wire of single bit. This is 8 bit bus. This is 32 bit bus of wire type, 1 bit clock, 41 bit virtual address, and you can define this high followed by low address or low followed by I. Usually we follow 31 down to 0. So left number is the square bracket is always the most significant bit of the vector. And an example shown, this is the MS. Okay, so next vector part select. Now if you want to access this bus is 7th bit position, like 7th or 0 from if you start 7 will be the 8th location, and you are accessing 2 down to 0, 3 bits, least significant 3 bits. Again this is not allowed because it's in the reverse, should be always from the left of the specification, and 2 most significant bit. Okay, so memory, we have the word size and the array size. Like if we have say reg of x, this is a 1 bit location, 1 bit, and like this we have 31. So this is x. So this is the memory. So if you specify any range here, this way it will be, the number of bits will increase. So now if I specify range 2 down to 0, 0 down to 2, y. So now it is 3 bit. So I have 3 bits of data starting from 0 till 31. And this is the y. So this is a 1 bit of size 1024, 1k 1 bit word, and this is a 8 bit, so 1k 8 bit word. Okay, next parameter. So if we don't want to have say one code where we want 8 bit, and next code we want 16 bit, so instead of changing the entire, if we can use parameters by changing the this alone, and we can define what is the byte size. Has 8, so it will be a of size 8, 8 bit or 16 bit just by changing it. So just to summarize, this is a 1 bit wire, 8 bit bus, 32 bit 3 buses, 1 bit register, 32 bit register, and to define memory, this is a 4 bit 64 4 bit register, and this is how we will access the address. Mem A of address is the data, and this is a 1 bit 5 register, 5 1 bit register. And to define any numbers, it will be the number of numbers size, binary, hexadecimal, or octal, and the number. Okay. So now let's solve some questions. Consider the two statements. By default, all input ports are registered or S2 by default register is initialized to EX. So which of the statement is true and which is false? We have already seen the input ports are of wire type, so this is false. And register default is X. So this is true. Fine. Let's go to the next question. Match the following. So minus 6 tick D3 is a 6-bit negative number stored in 2's complement form. C. This is illegal operation. It should be minus 6 tick D3. And this is a illegal specification. This is a 6-bit hexadecimal number. This is a 32-bit hexadecimal number. Answer is 1C, 2B, 3A, 4D. So, any doubts? Okay. So, what is the VLSI design flow? First, we have design specification. So, what is the input, what is the output, what is the number of bits? Everything will come in the design specification. Next, behavioral description. Okay, from here to here, it should flow that control everything. RTL description. This is the HDL code. RTL is at the little higher level of coding, and here comes our gate level code. So in between, this will be done by the tool. So in between, like after we have a RTL code, we can have the testing test pattern generator at the RTL level itself, and also we can have the test pattern generator at the gate level. So this step will be at both for the RTL level code, and this will be at the gate level code. And uh, once RTL level, we will verify whether it meets all the timing, and it is synthesized to give a gate level description. Gate level, like uh, if we have 90 nanometer, we will have standard cells. It will map to the standard cells at the gate level. Next, we will have the verification at the gate level, test pattern generated at the gate level. Once this is clear, this design step is clear. If any error happens, we will go back to the RTL and modify the RTL code. Once this is clear, we will be performing the PNR, floor planning and place and route. So like if we have this is the gate, we need to connect this and this. So it will be a layout, physical layout, and if any issue with the physical layout verification step at the PNR level, we'll modify PNR, else we will modify at the RTL. Finally, we will get the implementation. After PNR, we will have the GDS2 format, which will be given to foundry to get the chip, tape out of the chip. So this is the flow of the VLSI design flow. So now what are the modeling techniques? We have behavioral, data flow, gate level modeling, and switch level modeling, which is at the transistor level. So it is at the very lower abstraction level, whereas behavioral is at the higher abstraction level. So let's see one example of a switch level modeling, where this is a PMOS transistor. So whenever this is 1, this will be off, this will be on. So this is on, the output will be 0. So for input 1, output is 0. And this is 0, 0, 0. PMOS will be on, this will be off. So this is 1. So this will be functioning like an inverter. And this is the CMOS, complementary MOSFET. So we call this as pull-up network and this as pull-down network. So this is at the switch level, and it is like this Verilog code is not synthesizable code. So if you have CMOS inverter, this switch level is usually not synthesizable. So module name not gate. So input followed by output. Input is X, output is F. Now internal declarations. Supply 1, which is VDD. Supply 0, which is ground. Now not gate. So first we need a PMOS. So this is the keyword here, PMOS. P1 is the name. We output and NMOS. End with NMOS. Clear? Any questions? So this is with respect to the switch level modeling, which is at the lower abstraction level. Next type of modeling is the gate level modeling, where we will be using the primitive gates, which are all these gates are defined in the Verilog, like for AND gate and OR gate or. So it's like output followed by the input, and we can also define the delay. Delays are not synthesizable. Synthesis means RTL to gate level netlist, which purely consists of the gates, and the name of the gate will be from the technology which it is mapping. So we will have the primitive name, delay, instantiation name, output followed by input. So if we want AND gate, a primitive name, delay, output followed by input. 1 unit of delay, in1 into out. This is the AND gate. And this is valid, but we need to write the instantiation name also after delay. So A1, this is gate A1, out, into its semicolon. So now using the gate level modeling, if we want to write the code for this gate level circuit, we have module, say simple circuit. So these are the port A, B, C, X and Y. So in this input is A, B, C. Output is X and Y, and wire is E. So AND gate G1, E is the output, A, B are the inputs, is the output, not gate. Again this is E. Sorry, not E. This is connected to the next input, and its output is Y. Next gate is OR, G3, X, E and Y. So in this way we can write the gate level code for this circuit. Okay, at the gate level we have more flexibility to optimize at the gate level, but as the number of gate increases, the lines in the code will increase and it will be difficult. So we go for the higher level of modeling. Okay, so anyway, we have one more thing. We have a 4:1 marks. So you can see how much big code we have, and further we will see the other modules like at the behavior data flow for the same 4:1 marks. So the 4:1 marks consist of two select lines, S1, S0, and four inputs, I0, I1, I2, I3, and output Y. So the inputs to the module are I0 to I3, S1, S0, and output is Y. So intermediate we have wire, so Y is not to Y3 and some negated output for the select line, and we have four AND gates, one OR gate. Okay. So with this, if you want to write the code for a 4-bit full adder, half adder, this is the circuit for the half adder. Sum is A XOR B, carry is A. We get a full adder by instantiating 2 times the half adder with a carry. So carry is like AB or BC or CA. And if you want to have 4-bit triple carry adder, triple means carry will be propagating to the next full adder. So we need to instantiate this is full adder 4 times. This complete is the full adder. Now to write the Verilog code for this, first we have to write a code for the half adder, which is XOR and 1 AND gate. Then write the gate code for the full adder, which is 2 half adder and 1 OR gate. Next we have to instantiate this full adder 4 times. So that we will have 4 copies, and here it is 4-bit A B. So we can each bit we can call by A of 0, A of 1, and then instantiation. Okay, this is with respect to the gate level modeling. Next, in the data flow modeling, we will be using assign keyword and the operators. Okay, so assign, what is the drive stem, if you want any delay, and the list of assignments. So assign output has operator we have used AND operator. So next we will see we have the logical and bitwise AND. So for this right hand side, this should be a 1. Okay, so the assignment expression is evaluated as soon as the right hand side operation changes and is assigned to the left side. So the left should be always a net, the right can be anything, net or wire. So if you want to model this in the data flow, so the operator, like if both are 0 0, it is I1, or 0 1 I2, 1 0 I2, 1 1 I3, and you can see the size of the code is reducing, and we use a ternary operator to define a 2:1 multiplexer. So if y, this is y, this is the select line 0 1. If it is true, it is I1, false, it is I0. Okay, this is 2 to 1, and this is the gate level for 4 to 1. Okay, now concept of delay. So we want to assign with the 10 delay. So delay in the continuous assignment, and we already know delays are not synthesizable. It is used in the test bench, or if you want to test any circuit with some user defined delay. So output will be appearing with the delay of 10. So till then we don't know what will be the output. So it will be in don't care. Again, this output will appear after 10 delay. Okay. So this is the delay of 10 units. Okay. So next we have operators like bitwise and logical. Okay, so arithmetic like multiply, divide, and logical like double, ampersand, logical and greater than, less than, equality, similar to C. And we also have bitwise operator like ampersand or, and some reduction operator, shift operator, and already we have seen this operation. Concatenation operation and conditional ternary operator. Okay, so now initial begun statement, these are the procedural blocks, and initial and begun executes only once, and they are usually for the simulation purpose, so they are not like synthesizable code. And now this block will be starting at the same time duration, only one statement, so no begin and end. So at time 0, this and this will all start together. That's why m is equal to 0 with the delay of 5, a is 1, and with the delay of 30, b is 1. So this is all with respect to this initial and this. Okay, why 30? This is a blocking statement, that is after completion of the first statement it will execute the second statement. So 5 plus 25, 30. Next it will all start with the same time stamp, so 20 and 25. 20, 10, x is 0, 10 plus 25, 35, y is 1, and at 50 we complete the execution. So next, always statement are synthesizable, so any changes in the sensitivity list, it will be executing it, so it will be running continuously, and this is used in the modules design. So all the always blocks start at the time 0, similar to that initial begin, and execute the statement in always continuously in a looping fashion. So now at the starting we want the clock to be 0. After a delay of 10 units, we want a clock to be complement of the clock. Again after 10, and this process will repeat till we reach 10,000. Sorry, not 10,000, it is 1000. Because we have given dollar finish. If there is no dollar finish, it will be running continuously, like an infinite loop. So now initial and always statement. So procedural block like concurrent processes are like concurrent processes. So in a block of this statement are executed sequentially, but all within 1 minute of simulated time, unless delay is specified. All blocks execute in parallel. Initial block execute only once, and it is not synthesizable. So it is used only in the test bench or for any simulation purpose. Always blocks are executed repeatedly, so it must have a timing control, otherwise it will become an infinite loop. Procedural assignments, the LHS should be a register and cannot be a NIT. We saw for assignment, this LHS should be a wire, but when we have a procedural block, we will have this LHS to be always rich. RHS can be net or wire or register. Okay, so event control in the sensitivity list, we will see how it can be controlled. So we can have a edge trigger. So if we have a clock, we want the statements in the always block to be executed at this edge. We call this as pause edge, and this is clock. But now we want the statement to be executed in this edge. This is called as neck edge. Okay, whereas level triggered, any level, like whether when A or B changes the state 0 to 1 or 1 to 0, this statement will be executed. Okay, so now this code we have already seen, which is the gate level code of a 4:1 multiplexer. And similarly, similar to that, we saw the code for the using the data flow. So instead of writing these many gates, it reduced to just a one line code of assign statement. Next, if we want to design same thing using the behavioral description, we will use a procedural block, always block. So this is the sensitivity list. If I0, I1, I2 or I3 or the select any one changes, we want the output to be computed. And for that, select, there are four possible select combinations, and we write the use the case statement. So this is the logic now. Okay, so now we saw that this is the blocking and non-blocking two statements we said. Let's discuss that. In Verilog, we have two assignment statements. One is blocking, the other is not blocking. So the blocking assignments will be executed in the order they are specified, and assignment uh, will block the execution of the statements that for, like if we have two statements, first statement will be executed, then only the next statement will be executed if you have the blocking assignment. Whereas in non-blocking, it is like having some extra buffers so that everything will be executed in parallel. It will not block the execution of the other blocks. So non-blocking assignments allow scheduling of assignment without blocking the execution of statement that follow in a sequential. So usually blocking assignments we will use for designing any combinational circuit logic, and if we have any sequential logic we will go for the non-blocking assignments. So if we observe here, this is some combo logic combination, no memory. So we will go for the blocking assignment. Whereas if we want a sequential logic, say this is like something like a shift register, and we assume that okay, this three we want, and we use the blocking, it will be like a simple buffers connected sequentially. So this is used to model the combinational circuit, this is used to model the sequential circuit. This is important. So which type of blocking or non-blocking you are using depends on the circuit which we want to design. So now A is equal to, according to blocking, first this will be executed. So A equal to 1. It's a buffer with A being 1. Next only this will be executed where B is A. After execution of this, only it will be executing where C is. So it will have a 3 sequential buffer. Whereas this will be converted to 3 flip-flops connected as a shift register. And we can avoid race condition by using non-blocking statements like now at the same time both the execution will start. So A will be trying to assign B, whereas B will be assigning A. But whereas here at the time t equal to 0, both will start the execution. It will be the previous value of A. Say A is equal to 10, B is equal to 20. It will easily like take this A to be 20, this to be, yeah. So it will take the old values of the RHS register. Order of the writes doesn't matter. Okay, so example, these are 3 blocking and 3 non-blocking statement. So we have a delay for the assignment, and so at t equal to 10, this will be 1, DA will be 1. At time unit 20 plus 10, 30, this will be B will be 0, and C will be 20 plus 10 plus 40, 70 will be 1. Whereas this will be directly at 10 units, directly 20 units, directly 40 units. When this starts at time 0, this also will start at time 0. Okay, so I hope this much is clear. Next, D flip-flop. Asynchronous reset means reset will not depend on the clock. When we have a clock, at the positive edge only, if reset is high and we can reset it, it is synchronizing with the clock. That time we will call synchronous reset. Otherwise, we will call as asynchronous reset. Okay. So here inputs are D, clock, and reset. So let's draw the D flip flop. This means it is a edge triggered flip flop. Clock. We have a reset and a D input. Q. Okay, so inputs are T, clock, reset. Output is Q. So whenever the clock goes from positive, our reset is going to the negative edge. We want to execute the following statements. That is, if reset is 0, so not of reset will be 1, so it will go to the if block. In this execution, we want Q to be 0. In this execution, we want Q to be D. So this is our D flip flop with asynchronous reset. And this is a sequential element, so we have a non-blocking assignment. Okay, so now we have a synchronous reset. Again, it's a positive clock. If it is a negative clock, we will put a bubble here. D input, Q, D, and reset if it is 0, so R a bubble. Now it is a synchronous because whenever there is a positive edge of clock, we have two conditions. RST equal to 0, RST not equal to 0. If it is equal to 0, so any doubts still here? So now if we want to design any uh, system, so we will have a data path and control path. So we have to design an FSM to have like control. If this is the first we will load, next if this is the state, the next state. So and the um, data path, say if x is between, we have to perform I plus plus, and if I is less than 10, we have to perform x plus y. So we need two adders for performing I plus 1, x plus y, and we need a comparison to perform whether I is less than or equal to 0, and again one more comparator, compare this one. So in this way, we in the data path we need some adder and comparator. Adder directly x plus y, and the comparator code. If it is like next data path, we need the comparator, two comparators. And what is the controller? If it is clear, after that we have to go to the load state, that state machine. If there is no output, either clear y, clear x. Okay, so now the code for the FSM, the control part. These are all the outputs, and this finite state machine. So every state we can have this 0, 1 and define in the case statement. So now combining both, uh, we have both the comparator and FSM. This is adder comparator from the data path and FSM from the control path, and this computation. So timing diagram wise, we can observe from the based on the control and the data path. So next we will see what is test bench. So to check any circuit design under test, we need to apply some test vectors, and the response we will be monitoring using the again in the test bench. So if we have, okay, this is like any submodule and a parent module. From here we will be applying the simulation. So test stimuli. Say inputs are so which is connected to G0 to G2 in the test bench, G3, and this is instantiated. And for the test bench, we don't have any port list. Whatever is the output here should become a wire here. Inputs will be the register. Okay. So delay duration between assignment for RHS to LHS. So this is called the inter assignment delay, or we are delaying the execution. After 10 unit, perform Q is equal to X plus Y, where it is simply wait for the approximate number of time step before executing. Whereas intra delay means here there is a delay. So it is delaying the assignment operation, not the execution. So value of X plus Y is calculated at the time that the assignment is executed, but this value is not assigned to Q until after the delay period. Say here execution itself happens after 10 units. Here X plus Y is calculated, but assignment happens after 10 units of delay. So that is the intra and inter delay. Inter delay is we have a delay of 5, then assignment. This means we have 5 units of delay. So B value comes to this value A after 5 units of delay. So till 5 units, B value will be in some temporary register, so that the changes in B for 5 units will not come. Like at 0, B is saved in a temp, but it is stored to A only after 5 units. Assignment is delayed. Now test bench. If we have some module design under test with 2 inputs, 1 output, and the output is IN1 and with IN2, and we want to test this, so the test bench will call this module and pass the values. Okay, so now come to the test bench. Monitor will help, it is a system task, will help us to see the value at that point, and $finish to stop the execution. Okay. So we can have some macros like define, include, system task like dollar time monitor to display, and finish will be to terminate the execution. So next we have a compiler directive, like we can define what is that, we say unit of time, right? We can define that as a time scale, whereas this is the reference time, and this is the precision, at what precision we can see the changes. So now this way means 1.5 unit into what is the reference time, 10 nanoseconds. So it is 50 nanosecond of time. What does this mean? 0.001 into 1 nanosecond. And smallest unit you can observe is 1 picosecond. So this delay we cannot observe because it is lesser than the precision. Next test bench. Let's okay. If you want a clock, 50% duty cycle means 50% on time, 50% off time. So Initially, we define a clock to be 0. Time 0 to 10 units. Then we define always to toggle. That is, clock is equal to complement of clock. So it goes to 1 for 10 units. Again toggles to 0 after 10 units. This should be a straight line because we don't have any rise time or fall time. Again it will go to 1. So this is 10 unit, and this means 20, 30, 40. This will be logic 1. Okay. You can define using parameter as 5 and delay will be half of, after half of the clock period, complement it. If you want variable time period like duty cycle, for some applications we may need some different duty cycle. So at that time this delay, high delay, low delay can be varied, which are defined with the parameter. So any changes here you can directly have generate any classic. FIFO is like a queue, first in first out. Again it's a register like memory of data width minus 1, which is 8-bit width and 32 such 32 8-bit register, and like pushing into the memory, popping means taking it to the data out. In sequential, so non-blocking assignment. So test bench, we have to call the FIFO. Okay, so Verilog coding guidelines like uh, any sequential logic, you should use the non-blocking assignments, and the modeling latches, non-blocking assignment. When modeling combinational logic, always use the blocking assignment. And when modeling both sequential and combinational within the same always block, use non-blocking assignments. Like mixing blocking and non-blocking will be a little difficult, so do not mix blocking and non-blocking assignment in the same always block, and do not make assignment to the same variable from more than one always block. If you do that, this will be the same, say x, it will say a node, it will be getting derived from this so if it is 1 0, it will be in the x state, don't care. So we should not drive the same variable from two always block. Okay, some questions. Assume the value of c is 0, a simulation time 0 for the below yellow code when the value of c will become 1. So the answer is D. Why 30? 10 plus 10 plus 10. Clear? Next question. Consider the two statements below. Which of the statement below is correct regarding S1 and S2? So S1 is switch level. Switch level is at the transistor level. So this is false. S2 is a data flow modeling. When we use that operator and assign, it is data flow, correct. S2 out must be reg. No, in the procedural block only, left hand side should be reg. For the assign, left hand side should be a wire. So it is B. Okay, going to the next question. Consider the statements given below. Initial blocks are not synthesizable. Is it true or false? And initial blocks are used for processes that must be executed more than once during the entire execution. Is it true or false? If it is false, then what is the correct procedural block? Q. Any answers? You can unmute yourself. Yes, please. If you are, will initial block be executed only once or will be executed multiple times? Okay, so initial and always are the two procedural blocks. Initial is not synthesizable and executed only once. If we have always block, it will be executed continuously, so like all the time. This will be like if we don't have any duration, we can use it as an infinite loop or loop. So S2 is true, S1 is false. Clear? Any doubts? Question 1, 2, 3. Yes. First question is the default value of S1 and S2. In these slides, we have seen that. Verilog components, yes. For any wire type variable, the default value is Z. Default value means you are not assigning, like you define any wire and you are for like, as we forgot to leave it assign anything, or for say there is some delay, some time the value is not assigned, or a net is hanging somewhere. Say consider in this design there is one net like this. It is just left hanging. This value outputs are connected through wire only now. Output by default is a wire, but output can be a register also. We can define like output reg A. Wire is like we have these two modules. We want to drive this module continuously. So we just connect through a wire. If we want this value to be somewhere stored and then drive it here, we will use reg. This is like continuous. Any doubts? I think you can unmute yourself if it is. I'm not able to get your question. Yes. I hope I answered your question. Is it clear? Yes. So by default, if we are not assigning any value, just leaving a net to like hanging value. So yes, the default value of a wire in Verilog is X, and the default value of a default value of a wire is Z. It's a wire. It's a continuous assignment. We left it to hang the like float. So it is at the Z, which is high impedance state, and nothing is driving that particular node. So in Verilog, it is Z. Whereas register, it's a element which is storing the value. For example, now by default, if nothing is assigned, its value will be in don't care. Default value of wire is Z. Is it clear now? I hope I'm able to answer your question. Yes, in Verilog, wire is like a continuous driving, so it is like hanging means it is at high impedance state. And register some element which is storing, so by default it is X. Yes, it is defined in the Verilog. So that's why the first question answer is the default value of register is X, it is true, and all the input ports are wire and output ports are wire. Yes, by default input and output are wire, but you can specify the output to be register, like using this keyword output range. By default, both input and output are wire. Okay, second question, it is with respect to the Verilog uh, number system. Like -3 is this is -6 -3, it is 6-bit negative number, and minus means it will store in 2's complement form. Next, where is synchronous? I think before this. So asynchronous reset means, first let's see synchronous reset. Reset is synchronized with the clock. Whenever the positive edge of the clock occurs, that time only whatever whether the reset is 0 or 1, it will check. If it is 0, then it will perform reset operation. If it is 1, it will perform the D operation. So the reset operation will happen only when the clock is at the positive edge. At here somewhere or at the negative edge, if the reset is 0, then the reset operation will not be performed. Whereas in the asynchronous reset, either the clock or the reset it will check. So if reset is 0, it will perform the reset operation independently. It will not see whether the clock is the percentage clock. And whether if the clock is going to percentage, it will perform the D operation. So in the sensitivity list, we have either reset 0, like negative edge of the reset, which is reset 0, or the positive edge of clock. So it is asynchronous, it is not synchronizing with the clock. Now is it clear? Synchronous means it should happen with the clock. Whenever the clock condition positive edge or negative edge is satisfied, then only the reset condition it will check. Whereas for the asynchronous, it will be happening independently. Either the clock changes or the reset changes. Positive means the positive edge and negative edge means negative edge. Code for synchronous. Yeah, code is, so whenever it is positive edge, then only this code will be executed. Now it checks if the reset is 0, it will assign 0, else it should perform the D operation. Like D, Q is equal to D. Okay, I hope the code is clear. Like whenever the clock is going from 0 to 1 positive edge, it checks whether the reset is 0. If it is 0, it resets the Q value to 0, and if not, it assigns the D to the 0 Q. Is it clear now? Yes, we will move on to the questions. Any other doubts? If you have doubts, you can unmute yourself also. Verilog, every variable with the type register flip-flop, it need not be. Tool will be defining it. So the based on the way we are using it, tool may make it to a latch, make it to a flip-flop. It depends on the, or sometimes it can make it to a buffer. The way we are using. When synthesis, the tool, after synthesis, the tool may give. These are the possibilities for register. So need not be flip-flop all the time. Clear? Okay. Third question, simulation time, we will start from 0, and for this to execute, it's a non-blocking, so 1 by 1, 10 plus 10 plus 10, 30. We will have the C value to be 1. Okay. Any other doubts? So next question, consider the below Verilog. What are the different data types in Verilog? Yeah, data types we have, firstly, for any intermediate values, wire register, ports input output. Then you can define parameters. Also, uh, int can be used if you are having any for loops and all. Otherwise, everything in Verilog it is going to be in binary, so it will be in the register or wire. So like all the processing will be happening in the binary, and any negative numbers will be happening in the 2's complement form. So wire and reg should be sufficient. For loops and all, we can use genvar or int for the loop variables inside the generate block. Clear? Float, we will be having a 32-bit representation, binary again. So processing will be like this can be used. Sorry, not for floating point. It is a variable of 32-bit, and for time variables, real time or time can be used. For floating point values, real keyword can be used, or we can define an wire of 32-bit. This will be an IEEE floating point format. Is it fine? Other than this includes wire, bridge. Clear? In the for loop, for the loop variables, we will use this integer, and another keyword is gener. For inside the for loop inside the generate. Clear? I hope I have answered your question. I have listed the data types and also a data type for float. Any other doubts? Let's move on to the question. Consider the below Verilog code. Let A and B be registers and clock be the input clock signal. Verilog, every variable with the type reg is a flip-flop means a false option only one. Where is that? Where is that question? It need not be actually. Okay. So here it is using a non-blocking assignment. So non-blocking, non-blocking. So there will not be any race because it's a non-blocking. The above code will not result in a race as the assignment is non-blocking. And the next question, in the above, what is the clock period? It is 0 initially for 10 unit and 1 for 10 unit. So this is the total period. Okay, so next question. Consider the statements below. Select the correct option regarding S1 and S2. S1 is inter-assignment and S2 is intra-assignment. We have seen delayed execution and delayed assignment, so both are. I think that is given in the slide. I will come to that question. Just a second. Next, consider the statement below. Select the option regarding S1 and S2. Okay, again, this is same repetition. Okay, ninth question is with respect to precision and delay. If we have a tick time scale, say 10 nanosecond, say precision of 1 picosecond, then what is this means? It is 10 into 10 nanosecond. It is 100 nanosecond. So now coming to the flip-flop question. Somewhere in slides it is mentioned flip-flops are different. Just want to show you. Yeah, register is not same as flip flop. It will sometimes registers will be converted to flip flops, but need not be all the time. Is it clear now? Sometimes it simple buffer may be sufficient, so tool will be. Yeah, register need not be all the time flip flop. Maybe flip flop sometimes, but not all the time. So any other doubts? Yes, if no questions, then we can end today's session. Any other doubts? If you have any other doubts, you can unmute yourself. Vectors, it is mentioned 8-bit bus. Where? Bus is this variable. No, bus is the name of the variable. There is no keyword bus. Wire 7 down to 0 is a bus of 8-bit. If you have reg 7 down to 0 bus, then it is a wire type here in this example. Yes, clear? Okay. So if no further doubts, then we can end today's session. Thank you so much for joining. Bye.